right? So the second time that I've given you, that is the quarter of time period. So you have to understand, as far as the circular motion is concerned, where the particle would have reached. Okay, so if we look at the motion, okay, so let's see, you're given the coordinates, is it? The x coordinate is 8 mv divided by qb. The y coordinate is 0. Yes, I think that is correct. But just check that 8 value. Okay. Something like this. So this is where the particle has started from at t equal to 0. So it would be here. Exactly. Because it's 45 degrees. So this is where it would be at t equal to t by 4. With a v perpendicular like this. So this x coordinate would be equal to r root 2. Okay, yes, now it is correct. Okay, so your r was mv perpendicular divided by qb. So into root 2 हो गया ये ना. So it is m into 2 root 2 v naught into root 2 divided by qb. So the x coordinate is 4 times mv naught divided by qb naught. The y coordinate is 0. And the z coordinate at that particular moment is how much? The z coordinate is equal to, now z coordinate in general is parallel component into time. So at t equal to t by 4, the z coordinate is 1/4 of the pitch, which is so pi by 2 mv naught divided by. So this is the position. So get the idea of this question. Okay, it's yeah. So Ananya, your answer was more or less correct. Just that small thing of should be 4 instead of 8. So you get the idea of it. Now the third part is going to be a little bit more complicated geometrically. So I just don't want to waste too much time on it, but just to get an idea of how exactly you'll solve it. Okay. So the third part is this time. So it is pi m divided by 3 qb. So third part we want to find the displacement from 0 to this. So just I want you to work out geometrically how that displacement will be looking like, and just a general method of how we would solve it. The exact numerical thing will be a little lengthy. Okay, so the third part, this time you can see is 1/6 of the time period. So 1/6 of the time period means your angular displacement for the uniform circular motion is how much? It is 30 degrees. Sorry, it's 60 degrees. Pi by 3 or 60 degrees. Okay. So that is why the question becomes a little bit complicated. Okay. So in this case now, what is happening is that the circular motion part, like this. Not a very well drawn circle, but doesn't matter. So this is where the motion started from at t equal to 0. It will be somewhere here. So this is pi by 3 at t equal to t by 6. Okay. So now it is about finding this one. You can see that this angle would be 15 degrees. Let's just come to this point P. This would be R. So that point P would have x coordinate equal to R cos 15 degrees, y coordinate equal to R sine 15 degrees, and z coordinate, of course, that would be equal to 1/6 of the pitch. And R, you know, the radius is so this is how we find it. So the displacement vector would just be xi cap plus yj cap plus z. And you know how to calculate cos 15 and sin 15 and all using whatever. You can use cos 30 plus 15 or whatever. So this is how you calculate the displacement. So hope this is clear, people. Similarly, if you wanted to find out the velocity at this point, you would see that the perpendicular component of velocity would be like this. It would be perpendicular to this line. So from that geometry, you could work out what angle it is making in the xy plane and work out its unit vector and all that. So this is a type of question that can be a little bit time consuming at JEE advanced level when it comes to helical trajectory. And as you know that in a uniform magnetic field, there are only two types of trajectory. Actually three, because you can project the particle parallel to the magnetic field. So it will be in a uniform 1D motion, or perpendicular, it will be in a uniform circular motion, and finally in this kind of manner, so it will be in a helical path. So that's this. Okay, now coming to my second question from this section. So that question is now like this, that we have a charged particle plus Q naught and mass m. It is dropped from rest. Okay. In a vertical plane. Which has a uniform gravitational field. And because of that gravitational field, our acceleration due to gravity, let's say, is minus g k cap, and a uniform horizontal magnetic field. Say bi cap planes. Okay, so for example, take this as our x-axis and this as our z-axis, or we can also consider this as our y-axis. So then we can consider the magnetic field. So magnetic field will in that case be coming out of the plane, whatever. So the particle will have a general type of path. So first of all, what is the trajectory of its path? And secondly, maximum speed and maximum vertical drop. Okay. So these two are assuming the particle does not hit ground. And the fourth thing is find the acceleration vector and the displacement vector at the earliest time at which its speed is equal to its maximum speed divided by root. So just try this question out next. No, Ananya, unfortunately, it will not be helical path with changing pitch. That would be the case if you project a particle with an oblique velocity inside magnetic field and gravitational field, which are parallel. But here, the gravitational field and magnetic field are actually perpendicular to each other. So just to give you a hint, the role of the gravitational field is just like a uniform electric field. So whatever analysis you've done before for electric and magnetic field combination, that same analysis can be applied over here. Hope you are following my point, okay? That exact same analysis can be applied over here, but only the case is that the two fields are perpendicular to each other and you are releasing the particle from rest. So now tell me what kind of path it will be in. So moving at some stage, you would have done the analysis for this kind of thing. If you haven't done, it's fine. We will do the full derivation. No, Bhagat, that's also not correct. Not part of parabola. Okay. I'll tell you, in fact, it is called a cycloidal motion. Are you people familiar with this concept of cycloidal motion? So that is that very interesting case where the particle undergoes a motion which will be in the plane perpendicular to the magnetic field. So that is in this case, which plane it will be the, yes, it will be the XY plane. Sorry, it will be the YZ plane. So magnetic field is along the X-axis. So it will be in the YZ plane and the particle's path apparently will be the same as the particle on a rolling object circumference. Even though it is not mechanical forces, it is in this case a combination of gravitational and magnetic force. Okay. So the reason why I picked out this question, people, is because the whole analysis is quite lengthy actually. So that's why we have to have some very well worked out shortcut methods for doing this type of question at the JEE level. Even for JEE advanced, if this is part of a paragraph question, you don't have time to do the full derivation of the cycloidal path and get the maximum speed and all that from that. So you have to develop a method of doing a sort of shortcut analysis and understand how to come up the particular questions which are asked by using that shortcut method. Okay. So I'm sure you have done this at some stage during class 12th year or whatever. So just try this out. Otherwise, I'll help you with the whole thing. Yes, the differential equation is a bit complicated to solve. So that is why what we have to do is you have to have the general analysis in mind for this. Okay. So I will do first the whole general analysis, then we'll come back to this question. Okay. So this is a very important special case of motion of charged particle. So let's look at this as a theorem first, then we'll come back to the question. So motion of a charge in uniform electric field perpendicular to magnetic field, and initial velocity is 0. So if we take the general case over here, suppose. So suppose we have a situation where we have magnetic field coming out of the plane. So let us say in a standard XY system, the magnetic field is BK cap, uniform and coming out of the plane. This is our coordinate frame. And along with that, we have an electric field, which is, let's say, vertically upwards. So we'll come back to that question. It will just be a sort of application of this concept. Okay. And now what we do is we take a charged particle and we release it from rest at the origin. So QM is here at t equal to 0. Its initial velocity is 0. So what you see is that initially the net force acting on it is just going to be electrostatic force. So there is the initial force that acts on it. So it's just QE. So in this case, it is QEJ cap. So it has an initial acceleration of QE by M along the vertical axis. Okay. But as it picks up velocity along the vertical axis, now the magnetic field starts pushing it along V cross B. So that will be along the x-axis initially. But as it develops an x component of velocity, the magnetic force will vary in direction. So we can see that it will have a trajectory which is restricted to 2D because there is no force along the z-axis. The magnetic force is always perpendicular to the z-axis and electrostatic force is constant along the y-axis. So there is never a force along the z-axis. So the motion is restricted to 2D. And just by analysis of V cross B, you can see that it will start turning like this. So let us say at some time t, it's got a velocity vector which is like this V. So at this point of time now, the net force on it will change because there will be a combination of electrostatic force which is acting on it, and along with that there will be a magnetic force also which acts on this now. So this is the electrostatic force, and along with that there is also magnetic force. Now that magnetic force will be in this sort of direction. V cross B, we can see here, is pointing like this. So this is your magnetic force at that time t equal to t. So that is how the analysis works out, that suppose at time t equal to t, the velocity vector is some Vx I cap plus Vy j cap. Then the magnetic force acting on it becomes Q V cross B. So you can see that that magnetic force will become QB into Vy j cap minus Vx I cap. When you do the cross product of this with k cap, so I cross k, you can see, is minus j, and j cross k is plus I, like that. So we'll get this. And the electrostatic force acting on it is, of course, QE cap. Okay. So it's acceleration vector which becomes the net force divided by mass. So the acceleration vector becomes like this. Q by M. Now we will have just a minute. Something is wrong here. The y component should be negative and the x component should be positive. So let's see if I got it correct. So I cross k should give you minus j. Yeah. So this is just so you can see that I cross k is minus j, so that's minus j here, and j cross k is plus I, so that's right. So I think that should be correct now. Okay. So anyway, so this will be b vy I cap plus e minus bvx j cap. Okay. Or we get what is called as coupled differential equation, that is x component of acceleration, which we can write as dvx by dt, that actually depends on y component of velocity. You can take this as one equation, and y component of acceleration is dependent on x component of velocity. So this system is called a coupled differential equation because the two variables are coupled, Vx and Vy. Rate of change of Vx depends on Vy and rate of change of Vy depends on Vx. So whenever we have a coupled differential equation, the way to solve it is we differentiate one of the equations one more time. Okay. So what we do now is differentiate equation 2. Okay. So on differentiate with respect to time. So we'll get second derivative of Vy. And why we're doing for the second equation is because it has a constant term. So we'll get rid of it. It will be more convenient. So it is minus QB by M into dVx by dt. Okay. And now substitute from equation 1. So you can see that Vy has a harmonic pattern. This becomes like a minus omega square Vy, where if you compare, you can see that omega is actually that term, QB by M. And from your magnetism, you'll remember that QB by M has the dimension of 1 upon time, because QVB has dimension of force. Right, so clear so far? So just substitute this thing over here in this equation. So you have this term inside the bracket, it becomes QB by M into Vy. So QB by M comes with a square, like this. Okay, so now once we are clear with this, next thing we understand is that, okay, Vy is some kind of an amplitude. So let's say that is some V naught, or we can take the amplitude as A only. We'll just understand it has dimension of velocity into sine omega t plus phi, and therefore the acceleration's y component is A omega into cos omega t plus phi, where we know the value of omega, but we still have to get the velocity amplitude for Vy, that is capital A, and the phase constant. Now we can see that at t equal to 0, initial velocity was a null vector, so Vy was 0. So that means my A sin phi is 0. And at t equal to 0, my acceleration vector was just the electric field's acceleration. So it was QE by M j cap. So acceleration's y component was QE by M. So that means A omega cos phi is equal to QE by M. Just don't confuse the phase constant with the charge. Just be careful of the symbols. So anyway, we will develop a shortcut method as we complete this. So we don't have to do all this analysis in the exam. Alright, so this is telling us that sin phi is 0 and cos phi is positive. So that means phi's value we should take as 0. So cos phi becomes unity. So we have A equal to E by B. Because we already had omega equal to QB by M. So just substitute cos phi as unity here. Omega is QB by M and you got the velocity amplitude. So now we got the complete picture about the velocity's y component. We can see Vy is equal to E by B into sine omega t as a function of time, where omega is QB by M. And by integrating this, we will get the y component of displacement also as so sine omega t's integration will become minus cos omega t, like that. So we will get 1 minus cos omega t. So I'm not doing the integration over here because I know you can do it. So just cross multiply and integrate. So dy will be Vy into dt. Integrate this from 0 to t, integrate this from 0 to y, and we'll get this, okay? But actually even that is not necessary here. What is more important is, so you can think of y as some kind of y maximum. Actually it's more like y maximum by 2. So from this you can see that the y coordinate varies between 0 and 2 times E by B omega. Therefore, the maximum value of the y coordinate, and substituting the value of this, you can see that is 2 times. Now omega was QB by M. So this becomes QB square by M. Okay. So we'll come back to a shortcut method for this also. Now let's come back to the x. Okay, so from equation 1, our dvx by dt was how much? It was q b by m vy, or that's becoming here omega, that is qb by m, into e sin omega t, because we are substituting omega as qb by m and the velocity amplitude for the y component as e by b, like this. Okay, so now integrate this. Zero initially when time was 0, instantaneous Vx at time t. So you can see your Vx will become E times 1 minus cos omega t. Now this is what it's showing you, that it has a unbounded motion along the x-axis, because it never has a negative x displacement. Vx is always between greater than equal to 0. It never becomes negative. Okay, because E here is equal to E by B. So that means the motion along x-axis is unbounded. That is, Vx is never negative. In fact, so along the x-axis, it has a stop, start kind of motion. Now, if you look at Vx as a function of time, you'll understand what I'm saying. The x component of velocity is actually behaving like this. So the x component of displacement, you can see from the graph's area only, is not going to be restricted. So all the time the area is increasing. So if you integrate this, you will get the x component of displacement also. You will see x component of displacement is integration of Vx dt. So that will be this kind of thing. It will be E by V t. Okay. Minus something like this. This kind of term. Okay. Just a minute, people. I will join you. Right. So this is, so just let's verify this, that 1 minus cos omega t function when we integrate. So we'll get t minus sin omega t. So this is, sorry, minus sin omega. So anyway, again, this is not going to be so important. What is going to be important for us is just understanding the velocity. If you look at the velocity vector at any point of time, where the x component of velocity is like this, it is E by B 1 minus cos omega t, and the y component is E by B sin omega t. Okay. So this thing actually will show you that the motion is cycloidal. Just analyze this. So consider an object which is rolling with a uniform velocity along a horizontal surface. So if this is our horizontal surface along which this object is rolling, so let us say it has a center of mass velocity which is some v naught, and some angular velocity about the center of mass is omega naught. So v naught is equal to r omega naught. Okay. And acceleration is 0. Alpha is 0. Okay. Now consider the trajectory of this point over here. This particle. So suppose it was here at t equal to 0. Then after some time, suppose that particle has now come here, some time t. So you know that velocity of that particle will have a superposition kind of situation. you'll have to write the velocity vector as the superposition of the velocity of the center of mass whatever and the tangential velocity about the center of mass with the superposition of these two. So at some general time t, this particle would have a component of velocity. I mean, it would have a tangential velocity of r omega naught like this about the center of mass plus the velocity of the center of mass. So its general velocity would be the vector sum of these two, that kind of thing. So also, if you analyze carefully here, if this has gone through an angular displacement about the center of mass of theta, then that angle is the same as the angle theta that this r omega is making with respect to the horizontal. So in time t, that angular displacement is omega t. In this case, I'm writing it as omega naught t. So the velocity of that particle in the ground frame becomes the velocity of the particle with respect to center of mass plus velocity of center of mass. So written as a vector equation, this becomes r omega naught into this unit vector, which is minus cos theta I cap plus sin theta j cap. And this is of course v naught I cap, center of mass is velocity. So this is your velocity of the particle with respect to center of mass. And in this, of course, remember theta is omega t. So substituting all this, you see the velocity of this particle is of this type. It is equal to v naught 1 minus cos omega naught t I cap plus v naught sin omega naught t j cap. This kind of velocity is. And therefore the displacement of that particle is of that type. It is v naught t minus v naught sin omega naught t by omega. That is the x component of displacement. And v naught by omega 1 minus cos omega naught t j cap. So this is exactly fitting the profile of what we have seen above for our charged particle, even though this is not a charged particle. Okay. So this type of motion, by definition, it is called a cycloidal motion. This is a mechanical definition of cycloidal motion, that it is the trajectory of this kind of a particle. So as this particle goes from here, let's say the highest point somewhere here, and then back here, and then again. So this path is this kind of. And you can see that this path, it doesn't actually turn like this. It doesn't happen that way because the velocity never has a negative x component. It's always like this. It's always like this. And at this point, it has the maximum velocity, which is 2v naught. And at this point, the velocity is 0. Okay, every time. And the other thing is, okay, so these are, couple of, so this is the mechanics definition of cycloidal motion. Okay, this is what is the definition, that it is the trajectory or the path of any particle that is lying on the circumference of a rolling object, rolling without acceleration, that kind of situation. Okay. Now we come back to this and we see this exactly fits this. Okay. This velocity vector we had, it exactly fits this. It's exactly like this. So we understand, therefore, the charged particle is in cycloidal motion. Okay. Now to understand, now to answer quick questions like this, that suppose we are just given electric field perpendicular to magnetic field and the particle is released from rest. Now we just want to find the maximum velocity, the maximum component of displacement. Okay, so let's say, suppose we are talking about y max, because we know that the electric field is along j cap and the magnetic field is along I cap or k cap or whatever. So we just want to quickly answer these type of questions. So what we do for this is we don't do this full analysis. It's too lengthy. This is just background information you should know, because without this you can't even attempt the question. You don't know what kind of path it is, so you will not know how to find out that maximum speed and all these things. But over here what we do is we use a shortcut method. So the shortcut is like this. In the shortcut we make use of two things. One is the kinematics of cycloidal path. Okay, and the other thing we make use of is work energy. For the charged particle, I'm talking about the charged particle. Okay. Now first let us look at the kinematics of circular path. Of cycloidal path. Now the kinematics of cycloidal path is something you'll notice that when your charged particle, when your particle P is over here, center of mass is moving with a velocity v0 and omega naught. Okay. What is the acceleration of the particle? When it is over here, what should be the acceleration vector of the particle? Its velocity is 0. Velocity of the particle is 0 over here. But what about the acceleration? The acceleration is like this. Okay. Why? Because in center of mass frame, okay, the particle P is in UCM. With respect to the center of mass, it actually has a negative velocity, negative tangential velocity along this direction, and is doing circular motion with omega. So it has an acceleration vector pointed at the center, which is equal to this. Okay. Now what is happening? The center of mass frame is what type of frame? The center of mass frame here is inertial. Okay. Because acceleration of the center of mass is 0. So therefore, the acceleration of the particle P in the ground frame is equal to the acceleration of the particle P with respect to center of mass. And this is a centripetal acceleration. Okay. So that's how I understand that the acceleration of the particle P over here is omega naught square r or v naught square by r upwards. Like this. Okay. Now also, if you look at the particle when it has come to the highest point of the trajectory, so these are the two important things that we will use from the kinematics of this motion. Okay. All right. So by the time this particle has come to the highest point, so my particle is now here. This is half the time period or whatever. Okay. So its velocity has become 2v0 in ground frame. But with respect to center of mass, is still doing the same thing. It's doing the circular motion with omega naught. So the acceleration at this point is also the same. It is still v naught square by r or omega naught square r, but now pointing downwards. Okay. So this is the important trick that we will use from kinematics of cycloidal path. Okay. So this is our trick 1. Okay. And the second trick that we'll use is for the charged particle. Okay. And that is for a charged particle plus q mass m in perpendicular electric and magnetic field, okay, work done by magnetic field is zero, because magnetic force is proportional to V cross B. Therefore, the instantaneous velocity is dot product with magnetic force is zero. So power delivered by magnetic force is always zero, whatever be the path. Okay. So the work done by the electrostatic force is equal to the change in kinetic energy. So here, if electric field is along the y-axis, like we have taken, and magnetic field is along the z-axis or whatever, just excuse me for a moment, guys. So we'll just write the work energy equation over there. Yeah, so writing the work energy equation over there will tell me what. So electrostatic force is constant, no? So work done by electrostatic force is just dot product of force with displacement. So it will basically just be, so work done by electrostatic force is QE dot S, which will just in this case become QE into Y, because the electrostatic force is along the y-axis. Okay? So our work energy equation, this thing, this equation here, this will become that QEY is equal to half mv square, because it started from rest, okay, because u was 0. So this is the trick that we'll use. This is the trick that we'll use for y maximum also. So for So these are the two little tricks that we'll use in a question like this. If we were directly asked to find the maximum velocity or the maximum displacement along the y-axis, one is this trick, that if you compare the point where your y coordinate is 0, so this is x equal to 0, y equal to 0 for the particle p, to the point where the y coordinate is maximum. So the accelerations are equal but opposite, and their values are equal to v naught square by r. So that is one property, and the other is this one. Okay, so let us go back to our charged particle and apply these two properties quickly now. So we can see that a charged particle started from rest over here. Inside that, okay, electric field was EJ cap and magnetic field was BK cap. So we analyze that it is going on a path like this. That we have to do, whether the path is like this or the other way, that we have to do by the cross product and all that, understanding that. Okay. So here, when it started from rest, its acceleration would have been E like this, and this acceleration would have been QE by M. Okay. Now, wherever it reached the highest point, kinematics wise also we understand that at that point, the y coordinate is turning. First it was increasing, then it's decreasing. So dy by dt must be 0. That means the velocity must be purely horizontal. But if dy by dt is 0, the other component is maximum. It is having a maximum speed, okay, at the position where the y coordinate is maximum. Now, at this point of time, its acceleration will be exactly downwards and of same magnitude. So at that point, you can see that the acceleration will be magnetic force minus electrostatic force divided by mass. So it will be Q V max into B minus E divided by M. So comparing these two, so this is equation 1, this is equation 2. So comparing these two, we can see that you will get the value of V max as 2 times E by B. That's it. That's one thing done. Okay, and then use work energy. And secondly, work energy theorem. So work done by electrostatic force is change in kinetic energy. So QE into Y max, that is becoming equal to half m V max square. Okay. So that's my second equation. And now substitute this here. So we have QE Y max is equal to half m 2 times E by V ka whole square. Okay. So as you can see from here, you will get Y max as 2 times ME upon QB square, which we had also got from just the differential method, differential equation method earlier also. All these things we have got from the differential equation method earlier, but this is just to show you how we can get this by a very quick shortcut method. So now with the shortcut method I have, this is all I had to do. What I've done from this point onwards, below over here, this is all I had to do to find from here onwards. This is all I had to do to find Y maximum and V maximum. One equation using this property. Okay, that if you compare the starting point where your initial velocity is 0 to the point where it has maximum displacement along the electric field, you will see accelerations are equal and opposite in direction, equal in magnitude. And the kinetic energy, which has increased from 0 to this maximum, has come as a result of the work done by the electrostatic field. So that is the shortcut that we use. So going back to our question, where there's gravitational field, just replace the electrostatic force with gravitational force. That's it. You can even use conservation of energy taking into account gravitational potential energy. So I'll just leave you with this whole analysis for a bit of time, and you now adapt it to that question and tell me the answer that you will get. Okay. So I am leaving it from here, shortcut that we are using. So two things that we are using the shortcut. One is the kinematics of cycloidal motion. And in that kinematics, we are making use of the comparison between this point and this point. So at this point, velocity is 0, acceleration is this much, v square by r upwards. At this point, velocity becomes maximum, which is actually 2 times vcm, but acceleration is now downwards, and same in magnitude. Okay, so this is how we adapted this shortcut to our particular cycloidal motion now, which is for the charged particle. Okay, so hope this part is clear, people. So now I'm taking you back to the original question, and there is an interesting third part of the question where you'll have to adapt this a little bit further. But now you'll understand that if you have this background information and this shortcut method in mind, then you can actually solve this quite easily. So just try this out, people. No, so the thing is, you should not get overwhelmed with the differential equation. That analysis of the differential equation you should have done in a derivation before, like we've done over here. Now all that is in mind. So that at the exam level, you don't sit down to derive that path and all that. You just directly compare it with cycloidal path in mechanics, and you know what to do. Okay, people. So let's wind up this question now and move on to something else. So don't worry about the lengthy solution and all. I'll be sharing the whiteboard PDF with you, so you will get the full solution. So in this example, when we release the particle from rest over here, we had G pointing downwards, and we had a magnetic field coming out of the plane. That's how we had taken it, because the magnetic field was along I cap, and I cap here would be coming out of the plane. So that also you have to figure out from the geometry of the question. So the question had just given us the axis and the field as vectors. So what the question had done is just given that this is the y-axis and this is the z-axis. So we have to figure out that okay, x-axis is coming out of the plane using cross product, and the acceleration due to gravity is minus g k cap, and the magnetic field is b I. Okay. So if it starts from rest over here, you can see that at this particular moment t equal to 0, it has an acceleration pointing downwards, which is equal to g. Okay. But there is no magnetic force. Now, as it comes down like this, what will be the direction of v cross b here? It will be towards the right, sorry, towards the left. So this particle will tend to turn like this, or something like this. So let's say this is the point where it has maximum vertical displacement. So this is our Z max, which we have to calculate. And when it reaches this point, now we know that its velocity will become maximum in magnitude, and its acceleration will be like this. And this acceleration will be equal to magnetic force minus mg divided by its mass. Now, from the property of cycloidal path, we know that this is this. So we have our first equation from that. So if you just replace the electrostatic force QE with gravitational force mg, you understand that this is your maximum speed. So that's one part done of the equation. And the other part, the value of maximum displacement along the gravity or maximum vertical displacement, we get by work energy. So change in kinetic energy is equal to work done by gravity, because work done by magnetic field is 0. So using this property now, so you will get your maximum this kind. Got this. Now the third part which is remaining is we wanted to find what velocity and acceleration, right? Or displacement and acceleration, something like that. Acceleration and displacement as a vector. For the first time. So that will be in between the two positions we have shown. The lowest position where V is horizontal and maximum, and the starting point at the highest point above where V was 0. All right, so let us, anybody got the answer for this part? So, again, you can understand it with a comparison of cycloidal motion. Just do a comparison with standard cycloidal motion. You can see that in a standard cycloidal motion, the particle starts from here at rest. When it's here, the particle's velocity is like this for the first time, v0 root 2. And then, of course, when it reaches the highest point here, it is Vmax equal to 2 V0. Okay. So this is the time. This is the time when V is Vmax by root 2 for the first time. So you can see that during this time, the angular displacement is pi by 2. Okay. So the time should be equal to quarter of the time period, or pi by 2 omega. Like this. Okay. So anyway, so at that point of time, the acceleration vector will be like this. It will be at an angle 45 degrees. So coming back to our particular problem here, in our particular problem, the cycloidal motion for the charged particle is happening like this. This is the trajectory. So this is t equal to 0. This is t equal to t by 2 when p is equal to v max, which was equal to 2 times mg divided by u. Okay. So somewhere in between over here, the velocity will be Vmax by root 2 or root 2 times mg by ub. And at that point of time, the acceleration vector will be like this. It will be at 45 degrees to this, whereas okay. So you can see that that acceleration will have the same magnitude as this acceleration. Will have the same magnitude as this acceleration. So at this time t, which is t by 4, the velocity vector will just become like mg by qb minus k cap component and minus minus j cap, like this, and our acceleration vector will just be minus g j cap. Okay. And that you can also understand if you do it more fundamentally, because when the velocity is like this, Vmax by root 2, you will see that the magnetic force acting on the particle will be like this. The magnetic field was coming out of the plane. So your magnetic force will be like this, and your gravitational force will be like this, and their vector sum actually will become in this direction. The vector sum will give you an acceleration in this direction. So that's another something that you can work out. Okay. But the easiest method is by the kinematics of the cycloidal motion. So that is why this whole analysis must be very clear to you like this. नहीं, acceleration का magnitude बेटा g होगा. Okay, only the direction will become like this. It would have turned by 90 degrees. Okay, you can see here that between 0 and t by 2, it is turning by 180. So between 0 and t by 4, the acceleration vector should turn by 90 degrees. So it's turning from the direction of minus k cap to the direction of minus j cap. So again, JEE Advanced will pick up on things like your proper application of cross product direction, so that you know that it's turning towards minus j cap and not plus j cap as the time is going from 0 to t by 4 and things like that. Okay, so this is a very specialized type of question, particularly for JEE Advanced, but you should know this. Okay, so this is all right. So this is more or less what I wanted to discuss from this section today. Okay, charge particle in combination of electric and magnetic field. But when you are revising this part, do the revision of the other things also. That is, when the electric and magnetic field are parallel to each other, what kind of trajectories are possible? For example, you can have uniformly accelerated 1D motion. You cannot have circular motion because the electric field will continuously act. You can also have helical motion, but with increasing pitch or with non-uniform pitch. So that is the only section we haven't discussed so far. Okay, so that you can do. So now I will go on to some questions to do with gravitation. That is one of the topics that has been requested also. You also requested for modern physics and optical instruments and all that. But I would suggest one thing, that since all of you are, I think in my class 12 group, one of the groups, I think group 1 for geometrical optics. So if you just continue with that group, in another week or two, we'll be doing optical instruments in that. In any case, optical instruments is more a formula-based thing for JEE mains. So given that it is only for JEE mains, nothing very complicated, just formula-based questions will come. So I don't think we need to do it in this forum. If you attend the class, or even if you go through my video recording from the lecture, I will do optical instruments in, which will probably be next to next week in my class 12th group. That should be enough for your optical instruments. Similarly, modern physics, at some stage I will do some tricky questions over here at this forum, but the basic concepts of modern physics are very simple, so I'm not going to discuss over here. However, very soon I will be coming to modern physics in that class 12 group also, so you can go through my video when that happens. Right? So now we'll just go back to certain things in gravitation. So this is Earth. It has acceleration due to gravity at the surface of this much. Now what is happening is, from the surface, if we project a particle like this at an angle of, let us say, 37 degrees at u equal to escape velocity divided by root 2. Okay. So a particle is projected at u equal to escape velocity by root 2. At the surface of Earth. Okay. So it is projected at that velocity at theta equal to 37 degrees with respect to horizontal. You want to find the maximum distance from the Earth's surface during its trajectory. And for that, radius of Earth is given to us, 6,400 kilometers. And to find minimum speed during its path. And for that, the acceleration due to gravity at the surface is given to us as 10 meters per second square. So just try this out. Okay, people, so hope you have understood what to do in this question. This is a very standard type of question. It's just conservation of angular momentum along with conservation of energy. Assume the particle is of very light mass, so it doesn't have any bearing on the Earth. So Earth remains stationary in its frame. And you will just apply because gravitational force is central in nature. It acts through the center of the Earth. So whatever be the location of the particles, at some point of time, if the particle's location is here, if its position vector with respect to the center of the Earth is this, you can see the gravitational force acting on it. Be acting like this. So R cross mg is conserved. Plus half mv square minus so this is the general concept. Angular momentum and total mechanical energy are conserved. Now if we compare the point where it reaches the maximum displacement from the surface of the Earth, that is the same as from the center of the Earth, with the initial position, compare those two directly, we get both the things that we're looking for. So this u was escape velocity by root 2 in magnitude. And this angle theta was 37 degrees. Now from this, if it goes on a general path like this, you also know from Kepler's laws that the path will be elliptical with the center of the Earth at one of the foci. Okay, so the ellipse would have continued like this, but here it would actually hit the Earth because it can't penetrate the Earth really. So the motion would conclude over here. So wherever it reaches a maximum displacement, the velocity vector will become like this, and this will be the minimum velocity, minimum speed, and this would be the maximum. So conservation of angular momentum. So mu cos 37 degrees into r is equal to mv r, where v is the minimum velocity, r is the maximum velocity. Because only at that point this angle will become 90 degrees. So we have m into 4 by 5 r into escape velocity by root 2 is equal to mvr. So our first equation giving us that 4 by 5 root 2 right, that is the formula for escape velocity at the surface of the earth. So that is what equation 1 is giving us. And secondly, energy conservation. So this will become half minus 1. So that is minus half. This is what we are getting from our second equation. Now we can solve them as a quadratic equation and get our relationship. So for example, solving for r, we can just substitute v square so substitute v square as just a moment, I will stop the screen share and restart it because I am getting some software hang. Just hang on a second. Okay? So just continue with that calculation. I will back with the whiteboard. Okay. Right. So we were substituting the value of v square from here. So do that. So v square is 16 by 25 VMER by R square. So do that substitution here. This term becomes 16 by 20, rather 16 by 50. No minus sign. So right, so fairly easy equation to solve now. So minus half is equal to 8 by 25 R by R square, or RE by R square, minus 1 by R. So you get a simple quadratic relation, as you can see. So 25 R square So we got everything dimensionally correct. There's a 1 by RE. So minus 50 plus 16 R square is equal to 0. So this will become how much? 9. So 3 by 5. So obviously the negative root will not come. Yeah, what was that? So 2 GRE by 5 is not possible because that's less than radius of the Earth. So that actually corresponds to, if the mass of the Earth had been concentrated as a particle centered here, then the path would have been like this. So यहाँ पर भी एक point पे, V would have been perpendicular to R, but actually that route is to be eliminated because here it will hit the Earth over here. It never goes to a distance of less than the radius. So that is why the negative sign wala route will be eliminated over here. So R max will actually be 8 by 5 So now coming back to maximum distance from the center of the Earth, sorry, from the surface of the Earth. From the surface will just be that distance from the center minus the radius of the Earth. So that will be 3/5 of radius of the Earth. So understood the significance of that second root now, because basically this system is just solving for when V is perpendicular to R. So technically speaking, just from the interaction that we've seen, if you replace the Earth with a super dense particle at its center, then it will actually complete an elliptical orbit around that super dense particle. If this was just a particle here, this would complete the elliptical path. So for that elliptical path, the minimum distance point would be here and the maximum distance point would be here. And those are the 2 points where V is perpendicular to R. So that is how we would be getting this. And then similarly, you put this back in the equation for V. So you'll get the minimum speed. Alright, people, so this should be clear. Okay, let's move on to another question. Gravitation now. So we have a 3-particle system of identical mass lying at the corners of an equilateral triangle. So 3 identical particles in outer space maintain mutual distances of L in a circular orbit about the system's center of mass. So find radius, time period, and speed of the orbital motion. In terms of quantities which are shown on the diagram, that is small m and capital M. Sorry, small m and L. The mass of each particle and the length of the equilateral triangle shape. So to find this is pretty easy question, pretty standard. Let's work it out quickly. So it is like an adaptation of binary star system. You can think of it that way also. Yeah, got the answer. Asker, good. Okay. So we consider three particles like this. Now consider the system centroid. So they would happen to be in a circular path about the centroid. Like this, where at any instant of time, the velocities are tangential like this and equal in magnitude. So mv square by r should be equal to the net centripetal force. Now the net centripetal force for anyone will come out as the vector sum of the two forces that these are applying. So the mutual gravitation between any two particles is F. So this angle is equal to this angle, equal to 30 degrees. So this will become 2F cos 30, where F is gm square by L square. And of course, in this above equation, R is L by root 3. Because you know that it is basically 2/3 of the altitude. So anyway, let's substitute this now. So mv square divided by L by root 3 is equal to root 3 times, because cos 30 is root 3 by 2, gm square by L square. So we get this time period, and radius we already know. So L by root 3, yeah. The radius will be L by root 3. So, like this, you can adapt this to n number of particles at the corners of an n-sided regular hexagon. 6 particles for regular hexagon, 7 particles for heptagon, like that. So, n particles for n-sided regular polygon. You can develop that general method. Alright, so this is another type of question in gravitation. Okay, now let's go back to something a little bit more fundamental in gravitation. So we have a solid sphere with a spherical cavity. Solid sphere of density rho, uniform density rho and radius r. Now a cavity which is spherical of radius small r, where that radius is actually less than r by 2, is cut out such that d is the distance from the center of the original sphere to center of cavity. So show that the gravitational field inside the cavity is uniform. And find its magnitude. So again, this is like a standard theorem you should know actually, that this kind of situation gives you a uniform gravitational field. Okay, so done people. Your answer will come in terms of capital G rho, and you will not need all these terms, but the terms given are r, small r and d. These are given quantities. From that you have to find the magnitude of the field. Yes, Bhaskar, I think your answer is correct. Right, people. So let me quickly go through the explanation of this question. So here the concept we have to use is of course superposition firstly, but before that we have to understand that when we have a uniform solid sphere of mass m and radius r, or density equal to m divided by 4 by 3 pi r cube. Now inside a sphere like this, if I take any point which is at a position vector r with respect to the center, but the magnitude of that small r is less than capital R. So this is the center. So r less than capital R. The gravitational field at that point is then given by the formula minus gm by r cube r, or we can write it as minus. So now we can replace m by r cube with 4 by 3. So this constant into r. Okay. So this is the idea here. So with this formula in mind now, what we'll see is for our particular situation, we have the solid sphere with a spherical cavity, let's say. Now this is the center of the solid sphere, let's say O. This can be inside the cavity also, it doesn't really matter. As long as it doesn't coincide with the center of the cavity. This is the center of the cavity. Now let us pick a very general point, which is like this. So that general point is at a position vector R1, let's say, with respect to the center of the solid sphere, the original solid sphere. So this position vector is R1. And with respect to the spherical cavity center, the position vector of that point is R2. like this. And let us say the center to center vector this vector is, let us say, we just express it as a vector D. So it's the vector OC. And that arbitrary point inside the cavity is this point. So for an arbitrary point P inside the cavity, the net gravitational field will be the gravitational field due to the original solid sphere minus the gravitational field due to the removed small sphere. Or, you could think of superposition. The net field is now this much. So if I add the smaller mass over here, I'd get the field because of the original solid sphere, which is this. Okay? So this will become, now go back to that formula. Now both the original solid sphere and the spherical mass that I have removed have the same density. So this becomes minus 4 by 3 pi g rho R1 minus R2. So this will have this term into R2 and this will have this term into R1. So I'm just making use of this formula. Now you can see that R1 minus R2 is nothing but the vector D. So E is just it's a uniform field. So the field lines, we don't draw field lines as such, but at any point the gravitational field will be like this. So E is magnitude. Uniform field. So this is like an important theorem over here, okay? Both for electrostatics and for gravitation. If this situation is in electrostatics, as you know, this will have to be a solid non-conducting sphere with uniform charge density embedded inside it, and then you cut a spherical cavity in it. So inside that spherical cavity, you will have a uniform electric field. Okay, people, so hope this is clear. So with that, I come to a conclusion for today's session. So just a minute. So I've unmuted all three of you. Hope you have understood everything in today's session, more or less, people.
Yes, sir.
Okay.
Yes, sir.
Good. So all three of you are part of that class 12 group, right?
Yes, sir.
Are you part that group where we are doing geometrical optics?
No, sir.
Right. So in that we will be covering optical instruments, and the next lecture that we have on Sunday, we will be doing first of all more complicated questions with combination of lenses and all that. And the subsequent lecture we'll have next week after that, we will do dispersion due to a prism and then optical instruments. So all that will get covered in that already. Okay? And subsequently in that batch, we'll also be doing modern physics at some stage. So the theory part of modern physics you can get from there. But since you have requested for practice in modern physics also, in the next lecture that I have with you people over here in this group, we will do some questions from modern physics also. But I also want to discuss that part of mechanics where we are dealing with conservative and non-conservative forces and the relationship between potential energy and force by the gradient method. That internal conservative force is negative gradient of potential energy, and we'll extend that concept into both gravitation and electrostatics also, where we have field as negative gradient of potential. So that is one of the areas I want to focus in the next lecture. And probably if we have done electromagnetism this time, then next time we should also do some good questions in electrostatics, especially to do with application of Gauss's law and induced charges and conductors and things like that. So those are the areas that I am planning, and you can also put in the request for any other parts that you want to
Sure, sir.
discuss. Okay? So that's it. Yes, all the best, and I'll send you the video and the PDF so you can go through the revision of this. Okay,
Thank you, sir.
okay, all the best.
Thank you.